Okay, so let's look at number 5 from the homework. It's a trough problem. And what you see here is a triangular prism that has a base of a triangle, and then it has some depthness to it. So it has this three-dimensional piece to it. Okay? And to make it 3D, let's put that there. So it's a triangular prism. And the volume of this triangular prism is big B times H. Okay, that means big B is the area of one of the bases. And remember, on a three-dimensional prism, whatever the base is, this big B stands for the area of the base. And this is a triangle. So this big B is really 1/2 times base times height. We'll get to that here in just a bit. Because I already have an H here, I'm going to say that this H, I'm going to use the variable L, because it's just a length. And this L is representing this length right here, which over here on the picture is 12. Okay, so if I put in L, this would be my equation for the volume. Now, I ask myself, because I have the diagram, remember the acronym, the diagram, the rates given or unknown. But right now, A is asking us if water is being pumped into the trough at this. We know that dV/dt is a positive 2 because it's being pumped into, and it's cubic feet per minute. We're looking for how fast is the water level rising. So this level right here, we're going to call it H. How fast is this level rising when H is equal to 1.4 feet? Okay, so now we ask ourselves these two questions, because we have our equation as well, we have our rates, we have our equation. We've got to ask ourselves these two questions. From this equation, question number 1 is, does V change? And it does. The water level is obviously going to rise because the water is being pumped into it. Should we leave it as V? Yes, we need to leave it as V, because how else will we get this dV/dt when we differentiate? So the other question is, does B change? Remember, B is the base right here, which is right here, but it's also the base of the water. So the base of the water is changing. It's growing as you pump more and more water into it. It is growing. Okay, so again, that base is also changing. That base, which is in purple, I can color that in purple right here, this B is in purple, that's changing. Okay, let's do the height so that you can see all these pieces. The L right here is this one. That one's not changing. And because of the fact that it's not changing, I can go ahead and plug in a number right now. And that number is 12, because it's a constant. So if I plug in that number right now, I don't even have to worry about that variable anymore, because it's a constant. Again, remember, that's one of your questions that you ask yourself. If it's not changing, and you see 12 is the shape of this tank, it's still the length of the water no matter what. So we plug in 12 right now. So the only ones that are changing are V, which is the volume, B, which is that purple base, and we could say in orange, this height right here is H. So nowhere did we get asked to find dV/dt, nor are we given dV/dt. We're only given dH/dt. So we want to keep H. We want to make B turn into H. And chances are, with these triangles, you're going to have a proportion. And you need to look at the original shape of this tank. And you need to ask yourself, B is to H, the ratio of the base to height is 3 to 3. So the tank, this length was 3 feet. That's the base. this length of the height was also 3 feet. So base to height is 3 to 3. And yes, you can simplify this to d or b over h is 1, which if you multiply both sides by h, this is what I was wanting. Or some people might just cross multiply and get 3b is equal to 3h and still divide by 3 and still get the same thing. So if b is h, then I can go over here where there used to be a b, and I can now put an h. So that I will have h squared times 1/2 times 12, which would be 6h squared is b. So this is the simplified form of this equation that we were trying to get. Now we're ready to derive. The left side is dv dt. The right side, you're only going to do 2h dh dt. And then constant multiple rule, that's 6. So you get 12. And simplify to 12h dh dt. And now you just have to plug in numbers. 2 is a positive 2, which was dv dt, so that's going to go here. H, which it asked us that h was 1.4, that's going to go here, and now we can find dh dt. So if I plug in 2 is equal to 12 times 1.4 times, we could put x, I mean that's our unknown variable, and we're going to do comma x, because we could do a solve feature in the calculator, menu 3.1, we'll get our answer, which is 5/40 seconds. Okay. Part B is a little bit different. Still with the same equation though. The same equation as far as right here deriving to this 12h dh dt. So they're telling us that when h is 2.3, so we put 2.3 for h, we still have this 12. They're wanting to find out what is the rate at which the water is being pumped into it. So they're trying to find what is dv dt this time, because they're telling us dh dt right here. dh dt is rising at 3/8 inches per minute. But I've been doing feet per minute this whole time. So I need to do a little bit of dimensional analysis, and I need to change inches per minute into feet per minute. So the way that I do that, I do just real quick dimensional analysis. I know 1 foot is 12 inches. Those cancel to a form of 1. And now I have my, my units of measure, I have it written in terms of feet per minute. So whatever I have, I'm just going to divide by 12. Okay? So 3/8 is what they gave me. If I divide by 12, it's the same as multiplying by 1/12. This will reduce to 1/4. So I have 1/30 seconds. 1/30 seconds is this dh dt. And now, yes, I can just plug this into the calculator. This right here, when I multiply all three of them, I will get 69/80.